Currently, the world has lots of what they call light water reactors. Powering these light water reactors are these very, very small pellets, maybe a centimeter high, thereabouts. That little kind of pellet is the equivalent of 3 barrels of oil, maybe like 200 liters,
Wow.
maybe a ton of, low quality coal, or 800 kilograms of black coal, or just like, a tremendous amount of natural gas. The power density of uranium as a fuel is immense. Waste produced volumetrically is extremely small for the amount of energy it generates. You have nuclear power plants operating in the US, which has all its spent fuel in completely engineered, controlled, radiation shielded casks, just sitting outside the plants, not harming anyone, completely accounted for. In terms of the amount of human footprint of the waste generated from nuclear power, it's actually very, very small.
Well, I've watched Chernobyl on Netflix. Okay. I know how deadly your industry is.
If we eat a banana, there's
Mm.
potassium 40 inside the banana. If we take a flight to Bali and we, are up in the air with less atmospheric shielding, we're getting about 40 microsieverts. Okay. So to give some perspective, the average Australian will receive about 3,000 microsieverts per year. All right, which is actually lower than one CT scan, because when you're in CT scan, there's got all these X-rays, you're getting zapped in from all directions, and you're getting like 7,000 microsieverts in one hit.
Mm.
Okay, so when people are afraid of ionizing radiation, then maybe they should be not so afraid, because they just take a CT scan and not think twice about it.
Welcome to another episode of the Discernible Interviews. In all of our bios, I put a little line that says original discernible content will make you a better human. And I think the reason is because of conversations like this. We get to talk to some amazing people on this show. Today, we are talking to a nuclear scientist. I can't believe we have them in Australia. This is Dr. Mark Ho. He's the president of the Australian Nuclear Association in Australia. And in his day job, he works for the government, works for the ANSTO. What is it? The Australian Nuclear Science and Technology Organisation. So I'm sure today he'll say something like he doesn't represent the government, which is fine. But what he will represent is some good, sound, clear thinking. The science behind nuclear. What are we doing in Australia? What does the science tell us should we do? Should we have more nuclear? Because there's this funny thing going on in Australia I'd like to explore, where we're seen as sort of an anti-nuclear nation. And yet you look at the polls and you look at the public response, it seems we're not so anti-nuclear after all. So we'll get into all sorts of things over the next hour. Dr. Marco, thank you for joining us.
Thank you. Thank you, Matt. And thank you for the intro, and thank you for the invite. You're very true in that I do work for the government and the national, our national nuclear laboratory. But of course, coming on here today, all views my own. Currently also serving president of the Australian Nuclear Association. So that's a professional body that serves to talk to people like you in the community, talk to industry, talk to the government, and politicians, just, so to put some facts out there and get the nuclear profile up. Because yes, it is a very, very small kind of group of people that know nuclear in Australia. So yeah, let's get started.
Well, can I ask, okay, I'll do the interview a bit in reverse. Can I ask we're going to go into the science of, I'd love to learn about SMRs and the Australian case for it and so on. But first, I think people are going to be wondering, aren't you just from a big, well-funded nuclear lobby? This is kind of the green argument. And I just want to get out of the way at the beginning. How much of this is industry just pushing an agenda? And how much am I talking to just a straight scientist who's saying these are the facts that I see?
When people say that there's huge money behind nuclear lobbying in Australia, nothing can be further from the truth. Okay. I mean, I've been associated with this NGO, Australian Nuclear Association, which is all completely voluntary based, coming from scientists and engineers who are very passionate about the field and are just doing all this communication, public communication in their own time. So it's an avenue basically to have all that knowledge, embedded within industry, such as the mining industry, such as our national lab, but then having an avenue of actually communicating with the public because obviously ANSTO does not have any formal position on energy, doesn't make policy, it just advises the government. But in that, there's a huge amount of knowledge and basically professionalism inside what is really within stone's throw of the Sydney CBD. So yeah, when people talk about, like huge nuclear lobbying money, etc., like nothing can be further from the truth, really.
So how does that compare to mining? I've spent some time on mine sites in previous careers, and sometimes they do some good PR campaigns, shall we say? But the reality is, there's a lot of profit to be made in mining. Is there profit to be made in a nuclear industry in Australia?
I think currently, well, it depends on where you look in the nuclear fuel cycle. So in the industry, we talk about the nuclear fuel cycle, which is from mining to, possibly, fabrication of nuclear fuels, running a reactor. In our case, only a research reactor, but in overseas, we're talking about power reactors that provide, say, a gigawatt of steady amount of supply of electricity. And then you have, of course, waste disposal as well in the back end, right? Or maybe reprocessing and recycling of nuclear fuel. So sure, when we're talking about the revenue stream for mining industry, that's like I think it's huge. It's like a $500+ million industry. It's probably north of that now because uranium prices have gone up. But in the kind of mid segments of where I work, in the national lab where we run a little 20 MW research reactor that makes a lot of medical radioisotopes, the value is not really calculated in terms of profits, really. It's about the well-being of Australians because, one in two Australians will probably get some kind of radiotherapy from medicines produced at ANSTO. So that's a great thing. And it's not really like a price tag, so to speak. But I would say also the other intrinsic value of having a well-run research reactor and a nuclear laboratory that is wholly publicly owned is that it gives the country a level of understanding, a working knowledge of what nuclear reactors are. And of course, that allows us to contemplate the possibility of nuclear power in the future, or in the more immediate sense, having perhaps nuclear powered submarines, because we've demonstrated that we can do nuclear well and responsibly.
So okay. I'm thinking of Lucas Heights where I grew up, all over Sydney. We actually have nuclear operating in Australia, right? Where are they? How many do we have? Because I think there's a perception here that it's a big evil thing overseas that we don't want here, but we already have some.
Yeah, like we've actually, like in keeping with the best tradition of Australians, we don't really blow our own trumpet very hard. So, the people here over at ANSTO have been doing such a great job in having a continuity of nuclear knowledge, working nuclear knowledge. We're running the old HIFA reactor, which was in operation for 49 years. It was built back in, 53 and commissioned 57. And then that was shut down and replaced with the Opal research reactor, a 20 MW thermal research reactor that makes nuclear medicines and provides neutrons for science. But we don't really advertise that much. So internationally, to give you some perspective, I think there's about 280 odd research reactors. And the ANSTO's Opal reactor is like extremely well regarded because it's, first of all, a new reactor. It's got a very directed and purposeful direction in terms of making medical radioisotopes and neutrons for neutron science and doing things like silicon transmutation doping to make high quality semiconductors. But this is also one of the highest availability research reactors. So our target is 300 operating days a year, which is immensely high. It's about 80% of the year, right? So that's also the average of power reactors around the world. Its availability is about 80%. So these are really staggering figures. That's kind of world best, and so yeah, like we do have great nuclear capability, but as I said, we're very modest
So
about it.
Opal, is that at Lucas Heights in the Shire in Sydney?
That's right, in the Sutherland Shire, yes.
Yeah, and do we have any other around the country? Is that kind of our crown dual?
That's no, this is the only currently operating nuclear reactor in Australia. There had been previous ones. I mentioned Haifa, which is a UK design, and then also a very small one called Moata, which is the Aboriginal word for, I think, fire starter. Yeah. But
Okay.
that's been decommissioned, and Haifa is in the middle of being decommissioned.
Okay. So if we, this is what's perplexing me a little bit, right? So if there's not a whole lot of money behind getting nuclear up and running, as we've touched on, there does seem to be a lot of money behind renewables, and we've done a lot of. I hesitate saying renewables because maybe I should ask you a broader question: is there truly any renewable energy source on the planet today? Because I look at, I used to work for Tesla. I'm a big fan, but solar panels and wind turbines, there's a lot of waste in the production, and we've got to put it somewhere when it's end of life. Same with nuclear, coal. The end of life, I guess, is in the atmosphere. So, is there any truly renewable, and how should we be thinking about nuclear? Is it any different from the others in terms of wastage and renewability?
Yeah, so I think like renewables has kind of become synonymous with wind and solar electricity generation. Of course, look, I mean, with any energy production, there is always going to be some kind of human footprint, right? Or mining that's required to make solar panels, or spinning out carbon fiber blades for wind turbines. So in that sense, I mean, nothing is truly renewable. I mean, if you want to perhaps think of a little bit deeper as well, is that, I mean, uranium seems to be like a finite resource as well.
Mm.
But actually, it's the more it happens to be that the more they try and find more uranium, the more there is. It's just a question of like at which, what is your kind of like economic recovery point where you're willing to spend that X amount of money to get that uranium out of the dirt. Or, but you can even drag uranium directly out of or extract it out of the seawater. But at the moment, it'll be 10 times higher than the price of like uranium coming out of Olympic Dam.
Mm.
So it's all a question of, what you want to do in terms of your economic kind of balance sheet in trying to get your resources out of the ground and form it using energy in such a way as to make wind turbines or to make solar panels or to make nuclear reactors. So yeah.
So maybe, Mark, we should if you could take me through bit by bit. If we look at, we're extracting uranium from the ground in Australia, in much the same way we have to extract different precious metals and so on to make solar panels or Teslas, whatever. So maybe we could walk through the life cycle of nuclear. So do we currently extract it from Australia? Are we a big producer on the world stage? That's my understanding. We dig up a lot of uranium and we send it overseas.
Yes, so Australia has about 33% of the world's proven uranium supply that can be economically recovered. Currently, we are responsible for about 10% of the world's uranium supply. And, a good deal of that is actually coming out of a copper mine called Olympic Dam. One of the uranium's kind of like more of a side tailing, side effect of extracting a copper, but it's very, very valuable. So, I mean, it's pretty, I mean, it's been long established that Australia has lots of uranium, put it that way. Okay. And in that, we're already exporting a huge amount of decarbonized energy just from exporting that uranium. Basically, we extracted enough uranium to be the equivalent of what the whole, Australian Eastern Seaboard, the national electricity market, generates in terms of electricity per year. So that's a huge amount of decarbonized energy we're already exporting.
To where? Where are we sending it?
Oh, so we're just basically sending it into the supply chain. It might be going to Japan, it might be going to India to supply their nuclear power reactors, right?
Right. Right.
So, but at the moment, as you know, we have a ban federally and on a state level against nuclear power. So therefore, Australia is not utilizing uranium as a nuclear energy. Yeah.
And the energy density of it, I'm thinking about we're a land of houses and holes, as they say. We dig up our ground. So we dig up a lot of coal, but the energy density of uranium, I assume you say we have, 30% of the world's reserves. That
Yes.
must be enough energy for centuries. It must be incredibly dense and rich.
No, yeah, absolutely. So a very kind of okay. So to kind of like run it back a little bit, currently the world has lots of what they call light water reactors. Powering these light water reactors are these very, very small pellets, maybe a centimeter high thereabouts, called uranium dioxide. Okay, it's slightly enriched with uranium-235 to about 5%. But that little kind of pellet is the equivalent of 3 barrels of oil, maybe like 200 liters,
Wow.
maybe a ton of low quality coal, or 800 kilograms of black coal, or just like a tremendous amount of natural gas. So certainly the power density of uranium as a fuel is immense, and then as well the amount of waste produced volumetrically is extremely small for the amount of energy it generates. So that's a kind of thing that's not often talked about, right? Because when we talk about nuclear power, a lot of people, or some people, like to say, "Oh, what about waste? What about waste?" But the fact of the matter is, you have nuclear power plants operating in the US, which has all its spent fuel in completely engineered, controlled, radiation shielded casks, just sitting outside the plants, not harming anyone, completely accounted for in a completely well understood and engineered and administrated solution, right?
Mm.
So yeah, like in terms of the amount of human footprint of the waste generated from nuclear power, it's actually very, very small
So
compared to
this,
the alternative.
okay, one pellet, two
Mm-hmm.
barrels of oil, a ton of brown
Three
coal,
barrels of oil, yeah.
3 barrels of oil, or a ton of brown coal, 800 kilos of black coal. Now, this pellet, we're going to use it. We're going to somehow set it off in a fission reaction and then let that heat water spin turbines. Is that how it
Yeah.
works?
Yeah, so that's a really nice way of capturing the essentials. Is that it's a very, very over-engineered, well-engineered way of heating up water to spin a turbine. Okay, so to give you a few stats, right? Currently, nuclear power is responsible for about 10% of the world's electricity.
Mm.
There's about 440 odd nuclear power reactors around the world. Most of them, about say 360 odd, is what's regarded as light water reactors. So they're cooled by light water, just normal tap water. That's been, of course, very cleaned up with, up to a high purity. And what happens is that you've got uranium fuel, these uranium dioxide pellets, in very, very long tubes made of zirconium. And for the American designs, you've got these very small, say, 1 centimeter diameter fuel rods, which are put in this kind of bundle, 17 by 17, of these fuel zirconium clad fuel rods, about 4 meters high, and they all go into this very large reactor pressure vessel, and they put water at high pressure to prevent it from boiling, heating it up at about 300, 320 degrees, and that heat gets conveyed to a heat exchanger, which it then basically donates that heat to a completely sealed separate loop that actually boils the water, creates steam, turns a turbine, and then you're generating about, on average, 1 gigawatt per plant, per nuclear plant. So, one of these plants might be able to supply electricity for 800,000 homes or 1 million homes in the US, for instance. So these nuclear power plants are, really great contraptions, just creating heat, creating steam, turning a turbine, and then generating a huge amount of electricity. And it's on for about 90% of the year in the US, 80% around the world.
This is
Okay.
light water reactors,
This is the pressurized water reactor that I've described.
right?
There's another flavor called boiling water reactors where this design's even more simplified and you're just directly generating steam in the primary loop. Yeah.
Okay, and so you're saying what we'd need about 10 in Australia, with 10 million
Okay.
households?
You must have read some of my other stuff because,
No, I'm
yeah.
guessing. I'm
So
guessing.
yeah, no, but your background's good because, I mean, if you look at the national electricity market, that encompasses the 5 states, right? Um, from Queensland up north through to Adelaide, I mean, through to South Australia and down to Tasmania, I think the peak capacity is about north of 50 gigawatts, right?
Right.
But in terms of the base load,
Yeah.
which is the load that's already always required, I think it's about 16 to 14 gigawatts, right?
Right.
So say if you've got a AP1000 Westinghouse pressurized water reactor, that's about 1.1 gigawatts of capacity.
Right.
And, you multiply it out by, say, 12 or maybe 15, and that's your base load covered. Yeah.
So these pellets, as it's operating, before we get to waste, how many of these pellets are we going through in one of these power plants per, say, year or?
Wow. I mean, like we're talking about, well, we don't really think of it in terms of individual pellets. We think about more like in terms of fuel bundles. So if you got those pellets and you multiply it all out by, 17 by 17 by how many pellets per we basically swap out about a third of those fuel bundles every 18 months when they do what they call fuel shuffling and refueling. Because, again, getting back a little bit to the physics, you don't actually have a completely even burn up or the use of that uranium dioxide material. So you need to kind of like shuffle them around a little bit to give it a more even burn. And that's why they do this fuel shuffling to maximize the potential of that fuel. And so, you basically, you're basically taking out about a third of that core. So there's about 157 fuel assemblies from memory in the Westinghouse AP1000 reactor. But in the end, it's really not as much as piles and piles of coal ash and whatnot that's generated.
Well, what kind of volume would you expect out of the Westinghouse AP1000? What would you expect after, say, 12 or 18 months? How big does it look?
So look, I mean, like it's really no more than a couple of cubic meters in terms of because those fuel bundles are actually very, very compact, Yeah.
Okay, so you put it, it's a pallet. Put it on a pallet.
Well, I wouldn't just put it on a pallet. I'll put it into a. First of all, I have to give a little bit more background. I can't believe this is actually getting to such a technical deep dive. So usually a lot of people are scared of the technical, as in
not this audience.
Yeah, no, okay. But so when we do refueling, the fuel assemblies, they do emit still radiation and also decay heat. And so you have to keep that cool. And what they do is they transfer that fuel all underwater into a spent fuel pool, and basically they stay there from about 5 to 8 years, so that decay heat, can be removed safely before they're transferred into what's known as dry cask. So to give people some perspective, if you actually just round up all the spent fuel in the US, so the US has about 90 odd power reactors right now. But if you add up all the fuel assemblies that they've ever generated, as in all the spent fuel that's ever produced, you can basically put it in a football stadium three levels high. It's about 100,000 tons, a little bit lower than that. And that's all the fuel that they've ever used. So it's actually completely manageable. The US at the moment is still kind of wondering what they really want to do with that used fuel, because you can sequester it underground or you can recycle it, what they call reprocessing. Yeah.
Okay. So Australia is obviously going to have a far smaller waste if we went nuclear baseload. So what happens with these spent rods after they go into dry storage? Are they just sitting there having a little meltdown for the next 100,000 years? What does, like little controlled meltdowns in their concrete case?
No, nothing's melting. Nothing's melting at all. So like people like me, nuclear engineers, we do calculations to show that just by natural convection cooling, that's enough to remove all the decay heat after they've been taking out the spent fuel pool. But look, fact of the matter is, these spent fuel bundles, when they're in these dry casks, they're just sitting out in the open and they're just getting cooled by the breeze, and they're just not doing very much, not harming anyone. In some ways, they kind of look like modern art because you got all these kind of like concrete blocks just sitting out there. In say, for example, in Europe, one of the first what I call nuclear waste repositories have opened to actually take power reactor spent fuel. Okay. And yeah, so you can either just put them underground, like geological disposal. What happens is that they take the kind of internal kind of like steel canister that's got all these fuel bundles, and they put it in a copper overpack and they bury it in clay and about, say, 800 meters on the ground, and there they stay. But to the nuclear engineer, that's actually somewhat of a waste, because actually people don't know that there's still huge amounts of uranium inside those fuel bundles, and they can be used to power an advanced, what they call fast neutron reactor in the future.
Okay.
So if you've gone to all that trouble concentrating that amount of uranium, then it looks a lot more like a uranium mine than something that's waste. Because if you've got the proper kind of like processing facility, you can take out the fission products, which doesn't assist with the nuclear process, and then you can reprocess or remake new fuel. And that's actually exactly what the French have proven, because they actually run their power reactors with recycled fuel.
Yeah, I know because I've been doing it in a game on the computer called Factorio, where you reuse your nuclear waste.
Okay, cool.
Elon reckons he learned how to do space from Kerbal Space Program, doing orbital mechanics. So I thought I'd do some nuclear experimenting with Factorio. Mark, with the sitting out in the field, you've got these spent nuclear bundles. How close can I get to? Because you said it's not harming anyone, but isn't it irradiating around them? How close can I get before exceeding some kind of safe background radiation level?
Oh, look, basically you can stand right next to it, and the dose you're getting off is no more than what you're experiencing in terms of background radiation. So there's been plenty of journalists and pro-nuclear activists that stand right next to those fuel casks with a dosimeter, showing that they're not really getting any more than what's experienced from background radiation. I always take the opportunity to talk a little bit about ionizing radiation on these interviews, because people, they're usually scared about things they can't see. But natural, what they call ionizing radiation, or kind of nuclear radiation, is kind of just all around us. It comes from high energy particles striking the atmosphere, correct? From cosmic rays. It might come from some of the fission products from radioactive decay inside the Earth, such as radon gas. And so we're kind of experiencing a very, very light amount of ionizing radiation on a day-to-day level. Okay. So, for example, if we eat a banana, there's potassium 40 inside the banana. If we take a flight to Bali and we, are up in the air with less atmospheric shielding, we're getting about 40 microsieverts. Okay. So to give some perspective, the average Australian will receive about 3,000 microsieverts per year. All right, which is actually lower than one CT scan, because when you're in a CT scan, there's got all these X-rays, you're getting zapped in from all directions, and you're getting like 7,000 microsieverts in one hit. Okay, so when people are afraid of ionizing radiation, then maybe they should be not so afraid, because they just take a CT scan and not think twice about it. And
have you seen those charts where it expresses microsievert exposure in bananas? That's 10,000 bananas.
Well, it's not a very convenient form of measure, but sure, right? But I mean, there's medical kind of research to show that there's no increase in risk of developing cancer until you attain something like, 100,000 microsieverts averaged over a year. All right. But of course, in the nuclear industry, we're always trying to be extremely safe. So we do something called abiding with the ALARA principle, which is as low as reasonably applicable. Basically, how do we minimize the amount of dose that people are receiving in the day-to-day work in the nuclear industry? And so, it might be, say, legislated that, nuclear workers can't have more than 50,000 microsieverts a year, but we try to achieve much lower than that, maybe like, 10,000 or 15,000 microsieverts. Yeah.
All right. Well, I've watched Chernobyl on Netflix. Okay. I know how deadly your industry is. So Let's talk about that. What is the deal with, is it 5 Mile Island or somewhere in the US that had a meltdown, Chernobyl, Fukushima, all of that? What is going on in these circumstances? The big thing that Australians are afraid of.
Okay, so with 3 Mile Island, it was due to a valve being faulty. But the problem was that in the control room, it didn't kind of indicate it as being faulty. And so they were losing coolant in the primary loop without knowing, and that caused a partial meltdown. However, when I was describing the pressurized water reactor to you earlier, one thing the West does is to make sure that the core, the radioactive content, remains inside the building by building a very large containment vessel, which can take the extra pressure of anything melting or gases escaping. And so most of that radioactivity was contained in that reactor itself. And that's why, even though they had a partial meltdown at 3 Mile Island back in 1979, the other units were allowed to continue to operate, and they shut down Unit 2, of course. And of course, the additional story, we'll talk about that a little, is that they're recommissioning Unit 1 because they're hungry for power over in the US, over in 3 Mile Island. With Chernobyl, look, I mean, that was as bad as you can get in terms of how to not design a reactor, how to not run a reactor, why you should not do tests on a power reactor. So everything I think that could possibly go wrong did go wrong with Chernobyl, what they call the RBMK, or the graphite moderated water-cooled design. And first of all, people shouldn't be afraid that something like Chernobyl can happen in Australia or anywhere else apart from Russia, because it's only in Russia that they still run those reactors.
Well, Fukushima's oh, go on.
Yeah, so the other thing as well is that they never had a containment building around, they never built a containment building around that RBMK reactor. And so, when it went through a meltdown, a lot of that stuff went in the air. And because of that graphite, it combusted as well. So, none of our reactors, and none of the West like pressurized water reactors, has graphite in them. So that possibility is eliminated. Sorry, you were saying?
Well, what does that even mean? Before we go to Fukushima, the most recent one, I think people like see, even modern reactors can melt down. What does meltdown mean? Because earlier you described these pellets. I'm fascinated that you can take something out of the ground, which is fairly inert, I guess, if I dug it up. I'm a farmer, if I dug it out in my farm. But then somehow, what do you do to make it extremely hot, where it gives off all this energy and heats up my reactor for 10 years or a year or whatever? And then how do you make it so it's not so hot and it's sitting happy outside? You get these massive fluctuations in power from this little pellet.
So if you look at a modern kind of like pressurized water reactor, and you have, you're making about 1,000 megawatts of electricity. But to do that, you have to be generating about 3,000 megawatts of heat. Okay. Now, as a general rule, after you shut the reactor down, so maybe 6 hours after you shut the reactor down, the fission products, which are the elements coming out of the splitting of the uranium atom, they're all radioactive, and when they're decaying away, they're emitting energy, right? So if you add up all that energy, it's about 1% of the thermal power during normal operation. So 1% of 3,000 megawatts is about 30 megawatts of heat. So that heat still needs to be removed after you shut the reactor down. Otherwise, the coolant inside might boil, and at a higher temperature, the water might dissociate, and so you get a buildup of gas. And so those are the kind of dynamics that was what happened in Fukushima, because that was a boiling water reactor. And when the tsunami came in and took out all the diesel electric generators that was responsible for maintaining the pumps to keep, the water circulating and keeping the reactor cool, that basically went offline, and so they had a pressure buildup, and they didn't, relieve the pressure fast enough. And also they didn't, purge the core by pulling in seawater, which could have actually kept the reactor cool. But because of the delay in action, etc., you caused a meltdown. over inside the reactor. What we mean by meltdown is basically in the regulation is basically called regarded as core damage. So we're talking about the tubes maybe melting, the zirconium melting. And then so what used to be very orderly kind of like fuel assemblies basically becomes this kind of molten corium. That's the kind of industry word for it. But one of the important points to note is that the advanced pressurized water reactors, the Gen 3 reactors, they're all built with a large water reservoir on site. So just by gravity alone, using natural circulation, having cold water entrained into the core, and therefore the hot water flowed on top, that kind of natural circulation, that passive natural circulation by itself can keep the reactor cool and prevent core meltdowns.
Did they have that at Fukushima? That passive
They
cooling?
didn't, because that was what known as Generation 2 reactors, right? Instead of Generation 3 plus with the large water reservoir on site, such as in the AP1000 design. So another thing that people don't know was that there was actually a nuclear power plant that was closer to the epicenter of that earthquake in Fukushima that survived actually just fine because they had a seawall that was higher, so that repelled the tsunami wave. But then they also had the whole site located higher up, which meant that the tsunami didn't take out their diesel generators. So it's all about designing smartly and preventing such things as what they call beyond design basis accidents from happening.
Okay. So, side question. How do you shut down a reactor? How do you stop the reaction from happening, the main thermal reaction?
Okay. So the main thermal reaction, so heat is generated from the splitting of uranium, right?
Yeah.
So on average, when you split uranium, either 2 or 3 neutrons come out after 1 neutron goes in. So to start a reactor, you might have a neutron source, a source that generates neutrons that starts the whole reactor up. To shut the reactor down, you basically have to introduce a material that absorbs neutrons so that the overall production of neutrons is less than 1. For every neutron that's generated, gets absorbed by fuel or gets absorbed by the other materials such as water or your radioactive shielding. You basically put in a material such as like boron carbide or say hafnium, which absorbs neutrons, and that basically kills your nuclear reaction or nuclear chain reaction. So yeah, like we call them shutdown rods for a reason because they shut the reactor down.
Okay, so in the case we go back to Fukushima, I haven't looked it up. What's the fallout? Do you know what the devastation is?
Well, I mean, the fallout in terms of the consequences was definitely very high because there was all this land that was, contaminated and they had to like repatriate the soil and all this. But in terms of the fallout, it was much more limited compared to, say, something like Chernobyl, right? Because you didn't actually have the core just vaporized and then going up into the air. You just had, like the venting of hydrogen gas, which collected on the ceiling, and then that created an explosive mixture, and that kind of blew off the top of the building. But it looks very dramatic, but it's not as bad as it could have been if it was just the whole core just like being vaporized and thrown into the atmosphere. Nothing like that at all. So so this is part of the reason why it's a little bit challenging to kind of communicate to people, even though it looks very dramatic. It's actually not, just the core being aerosoled and just thrown into the atmosphere, so to speak. The containment did operate as designed because it kept most of that contamination inside the building. And of course, now they're dealing with the cleanup, which is immense. So this is the whole reason why we design reactors very well in order to prevent such occurrences from happening.
Okay. All right. Well, if I go to a bit about the fear people have about it, and then that'll probably lead us into talking about the new designs and SMRs and passive cooling and so on. But this is a scary thought for many. What if the thing blows up, and 3 suburbs across now is uninhabitable for 1,000 years? You've mentioned,
Hmm.
and I believe it's true, that most Australians are not anti-nuclear when you look at the polls. Is that accurate, do you think?
Yeah, that's very accurate. So I've been doing this ANA outreach work for about 10 years now. So I've actually tracked the fact that it's gone from, say, 40% might be pro-nuclear to about, on average, 60% of Australians having no background at all, or kind of in-depth knowledge around nuclear, saying that, yeah, they'll contemplate having nuclear power because they know, for instance, it's carbon free. It doesn't make CO2 when it's making power. And just by the evidence of international operation of nuclear power reactors, they know is extremely safe. So just
So
by
this
that
this
alone,
fear that I'm talking about is subsiding in the Australian mindset.
yeah, it is very much so. And I think also the fact that the older generation, they tend to kind of wrap, nuclear weapons around nuclear power as well, where they're actually completely separate things. So, a lot of that Cold War fear around anything to do with nuclear has a negative effect on nuclear power when people talk about nuclear power. And so, with the kind of like changing of the guard, the younger people, they just want solutions. They want to know, where am I going to get that power? Can we actually make a systems that's half economic? And nuclear power has been identified as being a valuable linchpin in the overall strategy to decarbonize nuclear power around the world. So the recent, COP28 over in Dubai, there were like all these signatures to, I think there were like about 14 countries, advanced countries that's pledged to increase their nuclear power about threefold. So in the US, about 20% of their electricity is from nuclear power. They might want to like triple that, to about 60%, because everyone wants to get to net zero by 2050. And you need a certain amount of dispatchable baseload that's also carbon free, but without the excessive cost of, overbuilding grids and overbuilding nameplate infrastructure and solar and wind, to have that reliability that's very, very much required on a grid. Yeah.
That's what I find strange. And I mentioned earlier that there seems to be a lot of money in the renewable sector, but only in solar and wind and stuff like that. Uh, if you look at, say, France versus Germany, so Germany just finished shutting down the nuclear end of 2023, right? Recently, in an effort to decarbonize and so on. Just not going very well if you look at their gas usage and whatever. Why is there this strong pushback amongst the greener parties around the world, but even here in Australia, against nuclear? Well, I don't get that unless it's just money.
I think, look, I think, unfortunately, I think there's a strong sense of kind of tribalism that's kind of embedded in politics.
Mm.
And I think, it's a large part of people's kind of brand or kind of self-identity to be, say, pro something and then to maintain in that camp, irregardless of facts or evidence and whatnot. I mean, I think there's been studies showing that the more you show people evidence and facts, the more kind of entrenched are they with their views.
Right.
So,
Wow.
yeah.
But this is interesting in Australia. So we have, for our international listeners, we have a centre right party led by a guy called Peter Dutton at the moment, who represents that boomer cohort that you mentioned, not exclusively, but there is a higher percentage of boomer cohort represented there, and yet he's the party saying let's talk about nuclear, and then every other party is saying no, no, nuclear is evil. So perhaps we're seeing a shifting of culture, and political parties are trying to play catch up to see how they can represent that shifting culture.
Yeah, I mean, I think definitely think there's a lag in the thinking in Australia compared to, say, our Anglo partners in the US and the UK and Canada, because I mean, all these three countries I've named, uh, they basically have a bipartisan pro-nuclear position in terms of having nuclear power to decarbonize. So one of the things that happened yesterday, for instance, was a paper that came out of the Department of Energy in the US, which is their kind of energy lab, basically said that nuclear power is a prime source of reliable low carbon electricity for the US. Okay. And this is recognized by both the Democrats and the Republicans. And so as in the UK, they have a bipartisanship position of having nuclear power because we're seeing, the new construction of EPR reactors or European pressurized water reactors in Hinkley Point C, for instance, and that's been going on for a while. So I think, in some ways, Australians are still kind of coming to terms with this. It's very encouraging to see one side of politics wanting to have a conversation around this to increase awareness. Because, yeah, certainly we seem to be a little bit out of step with the rest of the world in terms of the overall strategy to economically see the decarbonisation of the energy mix. Yeah.
So so at the opponents to nuclear you find in Australia coming more from the greener parties, is that the case worldwide? They represent, opposition to nuclear?
It's a bit patchy. So some places, Greens Party is actually pro-nuclear. So I think
Oh.
so Sweden, so Norway. But of course, you have mild Green parties in Germany, for instance, that are anti-nuclear, staunchly anti-nuclear, even if they do import nuclear power from France.
What do you make of that? When I raised that earlier, what do you make of Germany denuclearizing completely?
Look, I mean, it doesn't make any sense from a scientific point of view, right? When you are kind of almost like a landlocked country, you've got a little bit of sea on the top, but you're in the middle of the European grid. So that's actually a luxury because you can do such things as import nuclear power from France. But look, I mean, due to politics, they're shutting down nuclear power. And then at the same time, had been very reliant on Russian gas, which is a strategic exposure point. And then also, because now that they've got less gas, they've been forced to open up new coal mines or, recommission coal-fired power stations. And so, if you're a technical person, you're always going to look at the hard numbers, right? So what makes a grid green is this figure called the carbon footprint. So if you look at like the amount of CO2 per gram produced per kilowatt hour of energy generated, the France has an exceedingly low number, which is about 40 grams of CO2 per kilowatt hour, compared to, say, the Germany, which is struggling to get it lower than about 300 grams of CO2 per kilowatt hour. And even that is much still better than Australia's current maybe 500 or maybe somewhat less, because we still have about 50% of our electricity, say, generated from coal-fired power stations. So
Is that the case? Yes, go on.
So I mean, I'm sure the numbers are always going down because of the renewables, coming into the grid, but that's the kind of ballpark figures we're talking about. So the French, they accidentally decarbonized because as a national program, they rolled out like 42 reactors within the space of 15 years. And, they achieved this very, very low carbon footprint way before everyone else. And at the same time, was able to gain such things called an energy security, which is somewhat of a kind of key phrase nowadays, because now we're seeing deglobalization happening. And we're talking about, having a robust supply chain around the world for Australia. We are very fortunate to have so many energy options that in some ways we kind of find it hard to make a cohesive policy around energy because we have the luxury of kind of thinking about things rather than acting on things, I think. So
that's a good line. Thinking about things rather than acting on things. What is our energy mix coming from in Australia? So down in Latrobe Valley, recently we've been shutting down power plants for the last few years. Victoria is interesting because we've banned fracking down there in the Constitution, which is an incredible move by that Premier Daniel Andrews down there. Now, Where is our energy coming from? Because there's this big push in Australia to go solar wind, and we're ramping that up. It's everywhere. Flipping Elon's out here building giant batteries in South Australia. Uh, can we not just prosecute that, just push that button, solar wind, until we get to 90% solar wind? Will that work?
Look, I think with enough money, you can make anything work. But the question is, when are people going to be getting to a pain point where they say, look, this is just a little bit too expensive? Okay. So one of the interesting things is that, I mean, there's a huge narrative to push towards renewables as if it's completely inevitable.
Mm.
And this has been going on for like 5, 10 years, back when I was like going to some of the public meetings when, say, Malcolm Turnbull was in power, and there was an inquiry as to how to reduce the price of electricity. And funnily enough, I showed up, with our ANA cohorts, and I asked, how come nuclear power has not been contemplated? And funnily enough, I think I got the feeling that it was a rather political document and not really a technical document that they're after. Because by convenience, people can point to the nuclear power ban as a way of not even admitting it into conversation at all when it comes to policy making, which is somewhat of a bit of a head in the sand approach when you look at what's happening around the world. Okay, so
what is happening around the world? Let's go to new designs, SMRs. Explain that to me, because really what I'm trying to find out beneath all of this is nuclear cheaper or equivalent in terms of just fiscally to solar and wind? Because that's a big accusation, is that you want to spin up nuclear power plants in Australia and elsewhere, you're going to require billions of dollars and so on and so on. What's the truth here, and what new designs have we got?
I think the quickest way I can to say that is that, sure, nuclear power plants are expensive, right, compared to wind and solar. But of course, having wind and solar has additional costs, the fine print being massive, grid build outs, which isn't necessarily costed. Okay. When we're just talking about LCOE numbers of wind and solar. And also, you have to have basically a spinning kind of synchronous generation to keep the grid cohesive and producing. And so the more renewables or the more kind of wind and solar energy that you introduce into the grid, the more that task falls on the fewer and fewer coal-fired generation or gas-fired generation or nuclear generation of allowed. And so those things aren't properly costed when we're talking about the value of certain characteristics of a spinning synchronous generator like coal, gas, or nuclear. Now, the thing is, if you look at the DOE report that came out just yesterday, they compared a grid in the US having renewables only to a grid in the US having a combination of wind, solar, as well as nuclear. And the outcome was that their assessment is the grid with nuclear working in cohesion and complementing wind and solar was 37% less in terms of cost. Mm. So the overall cost is what people should actually be talking about, because when the consumer or when the factory gets the electricity bill, they're paying for the wholesale electricity price, which is the outcome of the mix of the energy that you're getting from everything. So when a lot of people talk about, solar's great, or like, I like wind, so I'm all for wind, or I'm a nuclear power guy, I love nuclear power, it's a little bit amateurish to just talk about one thing over another. Because to be sophisticated about it, it's about working out what is the lowest wholesale electricity price with the proper mix of all energy generation, not just one.
So the best mix for somewhere like Australia is probably going to be a whole bunch of nuclear base load. Would you need peaker plants, gas peaker plants, and a whole bunch of solar and wind about the place as well?
Yeah, so gas peaker plants are always very useful because by themselves they're very cheap. It's really the gas that's really expensive. So it doesn't matter where it's Australia or the US or Europe, they've always got gas peakers. But yeah, certainly most countries are looking at a solid kind of combination of a large amount of baseload nuclear, say 20% of electricity supply, and then a large amount of wind and solar. and then a large amount of maybe a few kind of gas peakers. What's funny as well, I'll tell you a little bit of story. About 5 years ago, I was approached by some uranium kind of buyers, and they were trying to gauge what the projected demand in China was for nuclear power plants and therefore uranium. And they forwarded me a bunch of academic papers about the future projection of nuclear supply in China. And usually, academics love to furiously disagree with one another. But in China, because it's like a central command control economy, a lot of the scholars basically are looking at what the central planners are thinking. And so all their thinking were in line. So papers about, say, 10 years ago was predicting like a doubling of nuclear power in China within 5 years. And so I looked at the stats, and China doubled their nuclear capacity from 27 gigawatts to just short, about 52 gigawatts by 2020, because they do everything in 5-year plans. Mm-hmm. And the projection was about 130 gigawatts of nuclear capacity by 2030. And so that's already more than what the US has currently, which is a little bit shy of 100 gigawatts. But they're also planning for about 500 to 540 gigawatts of nuclear power by 2050 to satisfy about 28% of their overall energy or electricity requirements by 2050. And then the rest, they're backfilling with a combination of wind, solar, hydro, gas peakers, maybe a few, but they're much, the majority wise, it's talking about wind, solar, and a sizable amount of economic storage in terms of hydro and nuclear. And guess what? The US are thinking about the same, and Europe's thinking of the same, probably overall.
Okay. Just want to make sure I get in this chat about SMRs and new technologies. Salt reactors. What are these things? This is your specialty, isn't it? SMR, from what I could tell from Google. What are they? Are they safer? Are they viable economically right now, or is this something my grandkids will be talking about?
No, you'll be seeing them come up in about 5 years, sure. So small modular reactors are basically the Western response of how do we actually get back into the nuclear game, because most of those large reactor build-outs, gigawatt size, probably like 30 years ago, right? Those supply chains have atrophied. And so, those large pressurized water reactors, they need large forges and things like that. So they were thinking, well, if we actually build smaller units, put it into a factory setting rather than burning out in the open, we can get the cost per unit down, and we can get a lot more output in terms of units. Yeah, look, I mean, it's a really good kind of analogy with the aviation industry, where they're producing large amounts of planes. But yeah, it's also yet to be proven, because they have started on this journey. The two leading designs, as you know, would be the BWRX, the boiling water reactor number 10, which GE is coming out, and which they're going to be putting 4 units in Canada over in the Canada. So yeah, it's going to be switched on, I think, before 2030. That's what they're planning. And the idea is that you're basically taking proven existing boiling water reactor technology or pressurized water reactor technology and shrinking it in the package so that you can build them in a factory and have the quality up and the price per unit down. So that's their strategy.
Yeah, but scientifically, just numbers, would you not lose a lot of efficiency because you lose the economies of scale?
Well, you're losing economy and size, but you're actually gaining in economies of scale if you're producing multiple units. So the idea is that if you produce, say, more than 6 units, you're already kind of like down on your cost curve due to your increased learnings, which is, what the French kind of did with their large reactor build-outs, you see.
Right. But in terms of the thermodynamics of it, rather than the fiscal costs. So the economies of scale.
The thermodynamics would be similar, because you're still turning a steam turbine, for instance. Right. But sure, like, your fuel burn up might not be as thorough, so that might take a hit. But you're basically trying to deploy en masse rather than trying to trying to optimize everything in the form of a very large reactor, which takes a long time to build. So it's basically a different strategy in terms of approach. The SMRs do exist. So the Russians, they've got like a floating SMR plant over in the Arctic Circle. And also the Chinese have an advanced small modular reactor that's like high temperature gas reactor that they've been working on for like over 16 years. It's called the HTRPM. It's basically two reactors feeding one heat exchanger that's making about 190 megawatts of electricity. And the idea is to eventually deploy that inland so that you don't need you don't need water cooling, it can be air cooled because the high temperature gas reactors, they can operate about 600 degrees plus. And when you're operating at such high temperature, you can air cool.
Oh,
so that's the advantage. Yeah.
So am I correct in thinking of it kind of like the petrol engine? If we just get a lot of volume through, a lot of iterations through, we'll get a lot of technological iterations and improvements. That's what we're doing.
Yeah. In some ways, like you can apply that thinking with anything. The thing is with nuclear, because it's such a serious endeavor, the regulator has a large part to play. And of course, when you have a system of checks and balances, everything takes more time because if you've got a reactor vendor and then they've got a design, they're submitting that design to the regulator, they're going to be going through the whole design from top to toe, and then there might be some design amendments and whatnot. And this iterative cycle, slows things down. But having said that, what's really interesting as well is that from the last, say, 50 years of nuclear power development, pressurized water reactors and boiling water reactors, they've become the main design responsible for global nuclear electricity generation. So the next generation, again, we're talking about high temperature gas reactors or small molten salt reactors or sodium fast reactors. Again, that'll take a while for the regulator to catch up in their thinking and to allow the operation of these reactors after a thorough review. Yeah.
And are we seeing, last question on that, are we seeing improvements in safety with these new reactors? These new designs?
Yeah, very much so.
Yep.
So, I mean, just based on physics, right? If you reduce your core from, say, 157 fuel assemblies in a AP1000 reactors to about 37 fuel assemblies at half the height of about 2 meters in the new scale small modular reactor, already the amount of decay heat you have to remove is much, much reduced. I think it's like 5% of what a large AP1000 reactor is. And just by having a smaller heat source, it's much easier to keep cool compared to a large gigawatt reactor, say. And so, that's why the small modular reactors are safer intrinsically, just because of the, basically the additional learnings and having all that passive safety feature built in on site, about talking about the large water reservoir that's usually on site to keep those reactor cool, just by intrinsic physics, by gravity alone and driving natural circulation. Yeah.
Dr. Marco, I look forward to my nuclear powered car in the next 30 years, as you've promised in this interview today.
I haven't promised such things.
What would I wouldn't be a good journalist if I didn't put words in your mouth. What would be your, just to close, I guess there's a changing in the guard, as you said. But the way you've described the state of nuclear in the world today, it feels almost inevitable that I don't know, I guess this disempowers people to do anything about it. But it sounds like Australia's going to be drag kicking and screaming into the nuclear future anyway, because the rest of the world is going there. Is that reasonable?
To tell you the truth, look, I've been in this game for so long. I look forward to us lifting the nuclear power ban, but I can't put any bets on us lifting the nuclear power ban still, because so much depends on politics, right?
We will for US Navy aircraft carriers and subs when they visit. Suddenly it doesn't matter. Well,
yes.
Yes. Dr. Marco, thank you very much for sharing your expertise on this. I hope that it empowers some of those Gen Z thinkers that we've talked about, the next generation, to have a more scientific approach to nuclear.
I'll give our little ANA conference plug. So we've got
Please do. Please do.
an ANA conference happening in Sydney next Friday on the 11th of October. So we've got a range of international speakers to talk about nuclear power developments around the world. So just check out our website, just Google search ANA, Australian Nuclear Association, for more details. Thanks.
So that's the best place for people to follow what you do, Australian Nuclear Association.
Yeah, we've got a webpage. Yeah.
Funding. Sorry. I know I just closed the interview, but this is just a tricky one here. If there's
Sure.
no money behind nuclear, as we've discussed, I'm not sure how it comes to be. I feel like we need that capitalist motive. I mean, that's why solar is succeeding so well. That's why everyone putting solar on my farm out here. There's just so many rebates.
Sure. The financial framework is very, very important for any energy project. So, but what's interesting of the nuclear space is because it's nuclear, there's always usually a large part to play for the government, like to give assurances that they're going to be putting in a solid, well-funded regulator, to coordinate all the interactions between the shareholders in terms of utilities, the general public, Indigenous peoples that might be affected, and also to give a level of financial guarantee, because precisely nuclear power projects maybe take about 8 to 10 years to build. They need some surety that you're going to get bipartisan support so that the project doesn't get shut down midway, and and the project goes bankrupt. So if you look overseas, a lot of the nuclear power builds started off with huge amounts of government support, in a way similar to what Australia has currently with renewable support from the government as well, from both sides of politics. So yeah, I think having a certain amount of government support for a nuclear project is really important because it serves to reduce the financial costs. You might be able to secure, a lower rate of interest for a nuclear power project. So overseas, we've been seeing, maybe like you can gain access to 3% of per annum rather than say 7% or 10%. The sky's the limit because people don't really know. There's no kind of precedent of financing nuclear projects in Australia. But I think the clever way of framing or developing a financial support from governments as well as like even from overseas, because say Australia were to think about having an American design nuclear power plant, their import-export bank would probably also be in support, because the Americans would have an interest in seeing Australia develop a more strengthened relationship on the nuclear front between the two countries. So, in many ways, nuclear builds is somewhat of a soft power play. We've been seeing Russia basically building the reactor at cost for different countries, but then kind of locking them into a 40-year kind of fuel deal where they can only source fuel from Russian supplies. So yeah, that's I guess that answers your question in a way.
Well, I think we're digging it up here, everyone. We're digging it up and we're sending it overseas, and at the same time, we are hitting ourselves with our crazy power bills. So it's crazy. Come on, let's do something with this uranium. Are you on socials, Dr. Marco? Do you post anywhere?
Oh no, I'm actually very shy on social. I just do my ANA.
A true scientist.
Outreach. Sometimes I post on X or Twitter.
What's your X handle?
I think it's maybe it's Marco Nuclear or something.
I'll find it. And I'll link it in the show notes below, everyone. And thank you to the people who support this podcast at discernible.locals.com. A few paid supporters there keep us on the air. And I'm going to hit end on the interview, but we're going to have a quiet little discussion on how I can build a nice nuclear reactor on my farm. Thank you for joining us here today, everyone.
Thank you for your laws there. Thank you. Thanks for having me.